Assalamu alaikum. Welcome again in the part of linear algebra. Today we'll discuss, as I said in the previous video, we'll discuss the linear operator. Just let me recap from the previous video. We said that in mathematics, if we want to study any branch of mathematics, first of all, you study the object itself, which is in our case the vector spaces. Then you go and study the relation between these objects, which is what we will discuss today, which is about the linear operator. So the linear operator is a relation between the vector spaces, in particular between the vector space itself to the vector space itself. So basically we can think of it as a function. If you know from your calculus course, you will have, for example, a function of x equal x squared. So basically you take a real number, which is x, and you send it to x squared. So we can think of the linear operator as some sort of function where it takes some vector and send it to a vector, in particular from the vector space to a vector space itself, because sometimes maybe you take it from a vector space to another vector space, but this will not discuss in general in quantum mechanics, or at least in this course. So as we said, it takes from the vector. This is a very important notation. So you have the function t, which takes an element from v to send it to another element in v. It's a linear operator if satisfies two important properties that we'll use a lot. The first property, that if we apply t on the summation, and a summation of two vectors, you can distribute it. So basically, write it here. So if we apply it, for example, to x plus y, you can distribute it. So you apply it first to x, then you apply it to y. So in this case, it's called, I believe, the distribution property. The second one, that we can take the scalar outside. So basically, if I write it in this notation, if we have alpha, let me write it, for example, 5x. So we can take 5 outside, 5t of x. So it must satisfy these properties. Now let's consider the first example. We have a linear operator from the C2 to a C2, such that t defined as the following. So it's take as a C2, so it has two components, and give you the first component of the vector. So let's show that it's a linear operator. So just to clarify the thing, how this operator works, for example, if we take t I1, it will give you I0. So this is how it's works, this operator. So to show that it's linear, first of all, we need to show that it is, if we take, for example, x and y, so two different vectors in C2. So let me write, for example, x, like x1, x2, and y, y1, y2. Then now if we apply t on the summation, so now apply x plus y, so that is equivalent to apply again to, I will take just the sum, so I sum the components. So it is x1 plus x1, and down here we'll have x2 plus y2, and by the definition of the function, it will just give me the first component of this vector, so it will give me x1 plus y1, and here I will have 0, and that can be written as x1 0 plus y1 0. But note the following. Let me add a page here, which is, so this is basically is what? It is t when we apply it on the vector x, and here we have t when we apply it on the vector y. So this is basically can be written as t when we apply it on x plus t when we apply it on y. So indeed it satisfies the first property. Now let's check that it satisfies the second property. So let me take alpha. Alpha here is just a scalar, so let me assume it's a complex number. So when you apply t to, for example, x, so we'll have something like this: alpha x1, alpha x2, which is equals to alpha x1 0, which again can be written as t when you apply it on x1, x. So it satisfies the second property. So indeed, this operator that's given is a linear operator. Now we have another example. As I said previously, that we have two important vector space in quantum mechanics, which is the Cn, which is in this case in the previous example, which is C2. And in this example, we'll discuss the second vector space, which is the continuous function, the space of continuous function. So here we have two important linear operator. So the first one I call it t, and the second I call it s. Again, from continuous function to a continuous function, and it is the following. The first one, it is the differentiation operator. So basically you apply to it, yani the input is a function and the output is the derivative of the function, and the second is the integration operator. So let me just show you very quickly that the differentiation operator, it is indeed a linear operator. So if we take two function, we know that we can distribute the derivative on them. And if we take, for example, alpha f, and we take the derivative of alpha f, so we can, this is just a constant, so we can take it outside, and we can take the differentiation. The same thing with the integration. I will not do it for the sake of time, but these are two important linear operators that you must to know. Now we reach to an important fact about the finite dimensional vector spaces. So let's assume that I have a finite dimensional vector space with a dimension of n. So since it has a dimension of n, so that means that we have n bases. We discussed in the previous video. So we have n bases. What does that mean? We have bases. That means any vector, my vector space, eventually can be written as a linear combination of these. So far, nothing is new. So my goal is having this vector. Let's calculate, or let's see what's the image under this operator, which is linear operator. So let's take this. So if we take it, let's apply t to my vector, and now we get something like this. So what I have done is just expanding the linear combination. So I'm expanding this. Now let's use the fact about this linear operator. So the first fact that we know, it is we can distribute it. So we have n vector, we can distribute it to each vector. In other words, it can be written as a1 v1. So this is the first term. The second term, a2, then v2, etc. until t at an vn. But we have another property, which is we can take the scalar outside. So we can have a1 t v1 plus until an t vn. And if we want to write it in a compact way, we can write it as a summation. So using the summation notation here. So we notice a very important fact about the linear operator and finite dimensional vector space, that it is, if we want to find what is the image of any vector under the operator t, it is only enough to find what is the image of t under the basis, which reduce the calculation much. So what we need to calculate just t at the basis, so we have n of them. So let's consider this example. So let's assume my vector space, which is C2, which we know that it is finite. And let's use the basis, these spaces. So we have the first basis, which is 1, 0, and 0, 1. And we can check easily that these are indeed bases. And let's assume that it is given for us that the image, or when we apply the operator, which is t, the linear operator on the first basis, gives us 1, 0. And when we apply it to the second vector, or the second basis, which is v2, it gives us 1, 0 also. So let's assume that we need to find what's the image of the vector 5, 3 under t. So how to do it? Notice that we don't know what is t, and what's t do to the operator, but we can still find what is this value. So notice that 5, 3 can be written as 5, 1, 0 plus 3, 0, 1. In other words, it can be written as 5 v1, the first vector, plus, or the first basis, v2, the second basis. Now, if we apply t to it, so let's apply t for 5, 3, we know that it can be written as 5, the image under, or t applying on v1, plus 3 t applying on v2. But it's already given for us what's the value of v1 and v2, or t at v1 and t at v2. So it can be written So I'll just replace these by the given. So it is 1 0 plus a 3 0 عفوا 3 1 0, which can be written as 5 plus a 3 0. So it is 7 8 0. So this is the first part of the question. The second part is said, let's assume that we have a general vector which is alpha beta. Find what is t at alpha beta. Actually, there's a mistake. I should be t. So what is t at alpha beta? Again, the same procedure. Alpha beta can be written as alpha v1 plus beta v2. So if I apply t on alpha beta, I will get alpha t of v1 plus beta t of v2, which is, if we simplify it, you will get alpha plus beta, and here we have 0. So basically, what's the role of this operator? If we apply any vector to it, it will sum the component and put it in the first component, and it will give us 0 in the second component. So this is the role of it. Notice that we found what is the role of this operator by just knowing how it's transformed, or how it's act on the basis, which is v1 v2. This is a very important and crucial fact of the linear transformation, or of the linear operator. Now we notice we can even simplify it, and here actually the main theorem of the linear operators, that if we have a vector which is v1 here is one of the bases, we notice that t, if we apply it in v1, it is still in my vector space, which is v, because remember t, it is from v to v. So t at a vector v, it is still a vector. So what does that mean? That means it still can be written as a linear combination of the bases, because this by definition of the meaning of the basis, that any vector can be written as a linear combination of them. So let's assume that I apply t, my operator, on one of the bases, which is v1. So since the whole object here, it is still in my vector space, it can be written as a linear combination of the bases. Okay, where this now is a coefficient, just any coefficient. Notice the naming of the coefficients because it's important. Here we have the first vector on the basis, so it's 1. So I put 1 here as a superscript. While here we have the first component, I put it as subscript. Okay. So for example, here for the second vector on my basis, as a superscript, I put 2 because it represents the second. And here 1 is represent the first component, the second component, and until the nth component. You go the same procedure until the n vector of my vector space. Remember, we are dealing with a vector space of dimension n. So we have n of them. So if we reach to n of the nth vector, so we'll have here the first component of the nth vector, the second component of the nth vector, etc. So now we can use the following fact, which is, let's apply t on v. We know this is, so it can be written, so let's assume that, sorry about that, so let's assume that v is a linear combination, but now I'll call it alpha. So alpha v1 plus alpha 2 v2 plus until alpha n vn. So the component alphas are the component of my vector v, so it can be written as this. We saw it in the previous slide. Now the following, can I write, and can I even simplify this such that can be written as some coefficient times alpha v1 and plus another coefficient times v2, etc. Yeah, it can be. So let me just expand this summation. So it is alpha 1, هذا summation, so I'm just expanding this. So it is alpha 1 t applying on v1 plus alpha 2 t applying on v2 until alpha n t applying on vn. So far nothing is new. Now here's the new thing. I will just substitute what is the value of v1 by this expression. So we know that it is equal to AA, then it is V1 plus A2, so it's the second component of the first vector, V2, until we reach to AN1 Vn. So this just, we are expanding this, the only thing. Now we can add plus, now we expand the second term, so we expand this one. So we have alpha 2, and then we have what? So we have 1, so it's the first component, but now we are dealing with the second vector, V1 plus A. So we have A2 to V2 plus, until we reach to the nth one for the second vector, and Vn, and we cross the bracket. Now we do the same thing until we reach to, so just let me highlight it. So this is for the second, this is for the first, and when we reach to the last one, this one. So let me just put here. So we have alpha n. Now what is t when you apply to an n? We have A1, so it's the first component of the nth vector, V1 plus A2, A2n, V2 plus blah blah blah, then we reach to ANN, sorry, V. So this is the last term. Now what our goal, as I said previously, that we combine all the V1s. So we have them here, these V1, we take them as a, sorry, we have them here. So we take them as a any common factor, and we see what's the prefactor, and what is this question mark. So if we do the same thing, I'll just do it for V1. We notice the following. So yeah, sorry, here it should be, I believe, alpha 1. Sorry about that, it should be alpha 1. So alpha 1, no, sorry, alpha 2, yeah, correct. Alpha 2, alpha n, yeah. So if we do that, we'll notice the following. My goal is just to collect what is the prefactor before alpha before V1. So if we do that, we'll get the following. We'll have alpha 1, A11 plus alpha 2, A12, so the first component of the second vector, and etc. And then we reach to alpha n, A1, so the one here is fixed, An, then finally we'll get our vector V1. So this is what is the question mark. So now we can put this in the question mark that we are seeking for. Now we can do the same thing for what's the prefactor. So we can do plus, and we're searching for the prefactor for V2. So from here we can see it clearly. So first we have A2, so the second component. So we have alpha 1, the same alpha 1. Then we have now the second component of the first vector plus alpha 2, and then we have the second component of the second vector, and we can do the same thing plus plus until we reach to alpha n, and we have the second component of the nth vector times V2. Now we can do the same thing. So until we reach to the nth vector, so I need to find out what's the prefactor before Vn. So if we do the same thing, we can guess it. So it will be alpha 1. So this is, so I'm taking these things. So we have alpha 1, then the nth component of the first vector, plus alpha 2, the nth component of the second vector, and etc. until we reach to alpha n, the nth component of the nth vector, V. Okay? Now we can rewrite it in a compact way. We can further simplify it. Notice now we have this, the component of TV. So this we have our goal is we started with TV, and we need to find the component of that TV. So we have the first component, the second component, until we have the nth component. Now it can be further simplified as the following. For the first component, it can be written as 1, 1, 1, 2. So far I'm just simplifying the first component, which is this one. So it's 1, 1 until we reach to 1n, and the whole thing is multiplied by alpha to alpha n. Now if we do the product, indeed we'll get back to this expression. But we know this is actually the vector v that we started with. Let me just show you. The vector v has the component alpha 1, alpha 2 until alpha n. So these are just the component of v. So it's the vector v. So this is for the first component. It can be written as this, and for the second one, so it can be written similarly, as you can see, 2, 1 until A2 n, and again we multiply it by the vector v, and etc. until we reach to the last component, which is A1, the last one, yeah, AN1, AN2 until ANN, and we multiply it by v. So in a more compact way, it can be written as some matrix, which has the first row as A11, A12, A1n, and then here we have A12 until A1n, and here we have ANN. All of it is multiplied by v. So we reach to a very crucial and important fact and theory in linear operators, in the theory of linear operators, that if we have a finite finite dimensional subspace or vector space, we can write T at V as some matrix, which is the red one, times V. So in other words, dealing with operator, it is equivalent to dealing with matrices. And the opposite is true. Dealing with matrices, we can associate with it any linear operator. So this is a strong fact, and then it simplifies the calculation huge, especially in quantum mechanics, as we will see many times. When you have a linear operator, we just convert it to a matrix and we play with the matrix. Okay. Now the whole derivation here is usually it's not important for you as a physicist, but the procedure of how to find these this matrix is important. Summarize it here by the following. So let's see what is this V1. Let's discuss the first column here. So we have for the first column we have A11, then A21, until we have A1n. But what is this for the first column? The first column is basically, it is T when you apply it on the first basis. Okay, so when you apply it on the first basis, you will get what? N component. So you basically put this N component here. So this is for the first column. For the second column, it's the same. So we have V and T and V2, and you put it here until we reach to T at Vn, you put it here. So this is the procedure of how you find the matrix that is associated with the operator T. So as I said, for any linear operator on a finite dimensional vector space, so it's very important to be a finite, we can represent it as a matrix. And this representation, this is a very important and crucial point. This representation of the matrix depends on the basis that we choose for my space, because as we have seen in the previous video, that the choice of the basis is not unique, and thus the matrix will not be, the choice of the matrix is not unique. But in general, we can represent it as a matrix. Now let's consider this example. And as I said, this is the procedure for it. So first you find what is T, the operator at the first basis, and you represent it. So you have this component. So these here, the first column, you have the component for the for T at V1, and you so on until you reach to T of Vn. You will see an example here. So let's assume that we have my vector space it is Cn, which has a dimension of n, and we have the operator. It's the identity operator. So it's the vector V to the itself. Find the matrix representation for this given this basis. So these are the canonical basis or the standard basis. So we have 1, all zeros, then we have 0, 1, then all zeros, etc. So first of all, let's find the first column. So the first column is, you take T and you apply it to the first basis, so V1, let me call it. So T at 1, 0, so it will be, because the identity, all zeros, and then we apply. So this becomes the first column. So it can be written, if you want, it can be written as 1 times V1 plus 0 times V2, etc. until times 0 times Vn. So these are the components. We put them as a first column of my matrix. So let me just put here M for my matrix. And the first column, we said that it is 1, zeros, all zeros. So now how about the second column? So we have V2, which will be just V2, which is, we can write it as 0 times V1 plus 1 times V2, 0, V3, etc. all zeros, Vn. So in this case, what we'll have, these are the elements of the second column. So we'll get, sorry, this is 0, by the way. So we'll have 0, the first one, 1, 0, and zeros, and etc. So until we reach to TVN, which is equals to Vn, which can be written as 0 V1 plus 0 V2 until 1 Vn. So these are the main components, and we put them here. So we put 0, all zeros except the last one. So we notice that the matrix representation, basically it is all zeros except at the diagonal, but this is the identity matrix as expected. So we have the matrix representation of the identity operator. It's basically the identity matrix. So now we reach to a concept called the adjoint of an operator. So we can think of it as somehow the inverse of the operator. It is not the inverse, but somehow we can think of it as the inverse of it. So let's assume that we have a vector space. So now we are in general context. It's not, should it be a finite? Could be anything. So we have vector space. If we take, so focus with this definition, if we take the inner product between these two entities. So the first one is T, which is the operator T applied on the vector V, and then we take the inner product with another vector U. Okay, so these are two different vectors. So this is equals to the vector V, and taking the inner product with another vector S on U. So basically what I have done, I move this operator and I make it apply to the second element or the second component of the inner product. Okay, so we move it, and when we move it, we are not guaranteed that maybe we have the same operator. No, we have different operator. I just call it S, and this is for all V and U on my vector spaces. So if we have this equality that we can move the operator to the second element in the inner product, we call S the adjoint of T, and is represented as the dagger. This is called the dagger. So we can rewrite here in a small that T, if we want, for example, V or X, like that some textbook do. So take X here and Y is equals to X. Now I move it to the other side, but it's the dagger, and this is for all X and Y in my vector space. So this is the definition of the adjoint operator. I know at the first glance it seems it's a vague definition, but we will see some cases which will make it clear. Now we consider the special case of V to be the Cn, so it's a finite dimensional subspace, and we know that any vector can be represented as a column vector of n component, and this is U, also it's a column vector of n components. And we know that the inner product from the previous video can be written as the following. So we take the one in the left, which is, we call it a bra, we make it a row, and then we take the conjugate of each element. The whole process is called the conjugate transpose, because as you can see, we are taking the transpose of this vector, the one in the left, and then we take the conjugate of each element. The combination of these operation called dagger. So if you take the conjugate of each element and then we take the transpose, we call it a dagger. So for example, we know that AB, if we take the transpose of it, T, you will take BT and AT. So you flip the order. So this clearly works if we take the dagger, because if you take the conjugate first, it will not change the order for the AB. So we'll get, so it will not affect the order. So the only one that will affect the order is the transpose. So we'll take B dagger and A dagger. Okay. And thus the inner product of V and U can be written as taking the dagger of the left hand side vector, which is V, multiplied by the column vector U on the right. So it can be written as the following: V dagger U. And also we have seen that for any operator on Cn, because it's a finite dimensional vector space, can be represented by a matrix M. So if we apply T on V, we can get, it's equivalent to multiplying the matrix M by the vector V. Now we reach to an important property here, or important fact, which is that if we have the adjoint of an operator, which is acting in a finite dimensional vector space, is just basically the dagger of the corresponding matrix. So let's show it. It's very simple. So let's start. Let u and v be any vector in my vector space, and let me write what is this quantity u and v. We know that it is equal to the matrix u and v. Or let me flip just to follow the notation. This is v and this is u, right? Basically, I replace tv by mv using this fact. Okay. Now by definition, I will take the transportation of the first element, right? As we can see, we take the transportation of the first element, or sorry, the dagger of the first element. So we take mv, the whole thing dagger, be careful, because the whole thing, it's a new vector. So we take the dagger of the one on the left, the whole thing, u. Now, if we use the property that we need to flip, so it's v dagger, m dagger, u. So this again, it's a vector. M dagger, it's a matrix. Applied in u, it's a vector. So it's a new vector which belongs to my v. But what we notice? We notice that v dagger, let me call this vector u prime. But this is what? This is the inner product of v with u prime. Let me rewrite what is u prime. U prime, it is m dagger u. But v and u are arbitrary. So this is work for all v and u. So we deduce that the adjoint is empty by the definition. Is the adjoint of T, because this is by definition. This is the meaning of the adjoint, that we can make it to the other side, but yeah, we can take it to other side with all u and v. Now we take an important subset of the operator, which called the self-adjoint or Hermitian operator. Usually in physics we'll call it Hermitian. So Hermitian operator are essential in object in quantum mechanics, as we will see inshallah. And Hermitian operator, if you have a Hermitian operator, this in quantum mechanics, that means you have an observable and a quantity that we can measure. And if you have a quantity that we can measure or we can observe, then it has a corresponding Hermitian operator. So that's why it's essential in quantum mechanics. So what's the meaning of Hermitian operator? It's simply that if T is equal to its adjoint, and that's why it's called in mathematical term called the self-adjoint, because it is the adjoint. Or if you want in matrices, it is if the matrix M, if we take the transpose, the conjugate transpose or the dagger, you will get back to the matrix. So let's consider Cn. Show that the identity operator is Hermitian. It's very simple. So we have two ways. The first way is using the matrices. We know that the matrix representation of the identity is what? It is all zeros except at the diagonal. So we have 1, 1, 1. Now let me take the dagger for it, or the conjugate transpose for it. So we'll have the first row becomes the first vector. So this is the first row. So it becomes the first column. So if it becomes the first column, so we'll get something like this. And we need to take the conjugate, but the conjugate of 0 is 0 and the conjugate of 1 is 1. And then we do the same thing for the second row. Get 0, 1, and etc. So you will notice that you will get the same matrix M. So it's a self-adjoint operator. Of course, we can do it by the other way, which is calculate this quantity TUV or TVU, TVU. But we know that T is, when you apply it in V, we'll get V because it's an identity. So VU. And we know that V can be written as TU because, again, it's the identity. So U is equal to TU. And this is work for all VU. So that means that T is equals to the T dagger. So both are equivalent. Another interesting example, let's V be the C2, and let's have the vector has this form. So it's take the sum of x1, so the first component, plus I, the second component, this is the one, and alpha times the first component plus the second component. And the question is, what's the value of alpha in order to make T Hermitian? So first of all, let us find the matrix representation for T. So how to find it? So let's assume that the basis is V1, which is equal to 1, 0, and V2, which is equal to 0, 1. So let's make our life simpler. Now let's apply T on V1. So which means that T on 1, 0, it is equals to what? It will equals to 1 alpha. Now let's apply T on the second vector. So V2, which will be, so that is 0, so it will be I 1. Now the matrix, as I said, we take the component of the first basis, and we put it as the first column, and then we take I. Okay. Now in order to make it a self-adjoint or Hermitian, we need to equate it to M dagger. So what is M dagger? M dagger, basically it is, you take the first row and we take the conjugate, and then we take the second row and make it the second column. So we need these to be equal to each other. So what we deduce, we deduce that alpha dagger, so as we can see, alpha dagger, sorry, the alpha, so the alpha dagger must equals to I, and the conjugate of I must be equal to alpha. So alpha dagger must equal to I, and alpha must be equals to minus I, because it's the dagger of I. So we deduce that alpha equal to minus I. Notice this equation is compatible. So if we take the dagger of alpha, we get I. So we have a value of alpha which make this operator Hermitian, which is minus I. Notice sometimes maybe we will not have this value, so maybe we'll have some sort of contradiction, which means this operator couldn't made Hermitian. Now we go to example 8, which is let V be the continuous function from A to B, and let H be a real valid function. So basically the value of H, so if we take H for any value, it is real number. And let's define my operator as the follows. So the operator is take any function in my vector V and multiply it by H. So H here is fixed. So let's show that T is Hermitian. It's very simple. First of all, let us calculate. So let f and g be any function in my vector space V. Now let's calculate what is T f g. So we know for function, it is the integration. I don't care about the limit. It's from A to B usually, of the conjugate of the first one. So Tf conjugate times g. Okay. And that is equal, let me just move this one here, is equals to the conjugate. What is Tf? It's basically multiply H f and you take the conjugate and g. Let's put the integral here. Here's the integral. Now let's distribute the conjugate. So we'll have H conjugate, f conjugate, g. But we know that g is a real, so it's equal to H itself, and we have f conjugate g. Now, since they are commute, so they are functions, so I can move H to put it here. So we can move here. So it's equal to f and hg. But what is hg? Hg is basically, so we have f conjugate, hg is t at g. So when you apply t to g, you get hg, because remember t is basically multiply the function by h. And this is, if you notice, is basically the inner product of f on tg. And we are done. So we show that for any function we have this quality. So we can move t from the left to the right without for any f and g, which means that t is equals to t diagonal. Now we reach to a point that we discussed through chapter 2, and we always we hear it, which is the eigenvalue and the eigenfunction, or the eigenstate or the eigenvectors. So eigen in German means proper. So that means we're searching for the proper values and the proper function or the proper state. So what do you mean by proper? This is the meaning for it. So let's assume that we have an operator t, and we have a lambda as a scalar. We call it an eigenvalue and a proper value of t if there's a non-zero vector. So there's a specific vector or a state such that if I apply the operator on that vector, I will get the same operator but with some scale, or with multiplied by some scalar. So that means this is an eigenvalue, and we call the corresponding eigenvector of lambda. So the eigenvalues and the eigenfunctions are essential, especially for the self-adjoint operator, as we will see. Now let's consider an example. Find the eigenvalue of t, which defined as the second derivative. So we know that the second derivative is also an operator, a linear operator. You can check it easily. And let's assume that my vector space is a subset of the continuous function from 0 to pi, but with this condition, that this function must vanish at 0 and at pi. So this is my vector space. So basically my vector space has all the function f, g, h, any function such that it is continuous for 0 to pi, and they are vanished at the boundary. Now let's find what is the eigenvalues for my operator t. So we apply t to my function f such that I will get lambda, where lambda is a scalar, f. But this can be written as what? As the second derivative. I just apply t to my operator f, which equals to lambda f. So basically what we have here, we have a differential equation. So we need now to solve this differential equation. So we have cases, be careful. So the first case, if lambda equal to 0, so what we will have df over dx is equal to 0. But we know that if you have a function which has a second derivative equal to 0, it's the linear function. So ax plus b, where a and b are just constant. Now they vanish at the boundary, so f at 0, which is b, is equal to 0. So we have f of x equals to ax, but also we know that f at pi equal to 0. So a pi equal to 0, which means a equal to 0. So that means f of x equal to 0, but that cannot be possible. Why is that? Because we say that v must be a non-zero in order to have the eigenvalue. Thus, lambda is not an eigen. Lambda equal to 0 is not an eigenvalue. It's not an eigenvalue. Okay, now let me just... In case if lambda is positive, for the case of where lambda is positive, strictly positive, so what we have d of x is equals to a positive quantity, lambda f. But we know that since lambda is positive, so I can write it as, for example, k squared. It's possible to where k is some constant, some real number. Okay, so it can be written as k squared f. But you should be familiar with this type of equation, which has the following solution. So f of x has a e kx plus b e kx. Now at 0, f f at 0 is equal to what? It's equal to AB, which equal to 0, so that means that A must equal to minus B. Now if we substitute back, so f of x equal to A e kx, sorry, this is a minus A e minus kx, which can be written, if you want, as A twice sinh of kx. Okay, now f at pi is equal to 0, so it is A 2 sinh kx equal to 0, which means that sinh k is always positive, so A is equal to 0, but that means that f of x equal to 0, which is not possible, as we said previously. We must have a non-zero vector, or a non-zero function in this case. Now we consider the case, which is the interesting case, which is when lambda is negative. So in this case, we'll have df over dx squared is equal to plus, it is, this is the differential equation, f, which can be written as minus k squared, f, because it's a minus, it's a negative quantity, and k squared is a positive quantity, so we can write it as like this. But we know the solution of this, which is f of x equals to a sine kx plus b cosine kx. And if we apply the condition that we have, so at 0 we'll have b cosine 0, which means that b is equal to 0. I'm doing it fast because I believe we are already familiar with it from the infinite square rule that we met in chapter 2. And at f equals to pi, we have a sine k pi is equal to 0, which means that k pi must equal to n pi, which means that if we simplify, cancel pi with pi, so k must equal to n. So the values of lambda, where n here is an integer, so the possible values of lambda, it is the square root of, because we said that lambda, it is minus n squared. So these are the possible eigenvalues of my function with the corresponding f of n. So let me call it lambda n, with f of x equals to a sine knx. This is the eigenfunction. So this is just a basic example of how to find the eigenfunction and the eigenvalues of an operator. Now we reached the eigenvalues of a Hermitian operator. So it's a special topic, and it's crucially important in quantum mechanics, because as we will see in the chapter 3, that the eigenvalue of an operator represents the quantity that we measure. So the first fact is that the Hermitian operator must has a real eigenvalue. Otherwise, doesn't make sense that we measure complex quantity. The second fact, which is also important for the eigenbasis, as we will see inshallah, that if we have two different eigenvalues, lambda 1 and lambda 2, and for each lambda we have a corresponding eigenvector v1 and v2, then these corresponding eigenvectors are orthogonal. So let's show, first of all, fact 1. Let's prove it if you want. Prove fact 1. Proof. Okay. So basically it's simple. Let's start first of all. Let's assume that we have t. When we apply it in v, we get lambda v. And we need to use the fact that t is Hermitian. So let's calculate this quantity. So we have v, t, v. But we know that tv is basically lambda v. And from the property, if you remember, of the inner product, we can take lambda outside, so we get v. Now, we know that TV using the fact that T is Hermitian operator, we can take it to the second vector. So we can take TV V. So we are using this fact. So let's evaluate this quantity. Let me get back to the red. So it is equals to lambda V. Now we can flip, but remember in a condition that if we flip, we take the conjugate. So in the red, that these are the properties of the inner product, while this part in the black, I use the fact that it is Hermitian. So I can take this outside in a condition that get V conjugate. But remember that V is basically, it's a real number. So V is, when you take the number, it's in particular, it's the norm square, if you remember. And similarly here, we have lambda V square. But now equate these. We have these two expressions are equal. So if we equate them, we get that. Sorry. So let me just make it clear. I'm equating this expression to this expression. So get lambda. We can cancel. Why is that? Because V is not equal to 0. Remember here that V is not equal to 0 because it's an eigenvector. So we can cancel and we get lambda star equal to lambda. But what does that mean? That the conjugate of lambda is equal to lambda, and that it is only if and only if, actually, if and only if lambda is real quantity. Because if you have a complex quantity, then that's not real. For example, if you have 5 plus 3i, the conjugate for it, it is equal to plus minus 3i, which is clearly not equal to 5 plus 3i. Now the second fact. Fact 2, we'll do the similar argument. So let's assume that we have T V1 equal to lambda V1 and T V2 equal to lambda V2. Now what I need to show, that the inner product between these two vectors is equal to 0. So how I can show that? Simply, I start with using this fact. So I will evaluate T V2, which I can simplify it as V1. I'm using just the assumption that T V2 is equal to lambda 2 V2. Okay? Since lambda it is here, so I can take it. Again, I'm using the properties of the inner product, so equal to V1 V2. Now let's do another equation, which I will take now T, I will apply it here. So I'll have T V2. Now using the fact that T is Hermitian, so these two equations are equal. This equation and this equation must be equal because I just move T and I make it apply to this vector. But it is Hermitian, so one of the factors of this Hermitian, so that is this equation holds. So if we expand, what I will get lambda 1 V1 V2, which is again using the property of the inner product. Let me just make it red. I can flip, take the conjugate, sorry, lambda. Yeah, 5. So I have V2 lambda 1 V1, something like this. So eventually I will get lambda 1 and V2 lambda 1 star. So I can now flip again. So I'll get V1 V2. But as we said, these expressions are equal. We have here the equal sign. So this is equal to lambda 2 V1 V2. Now take it to the other side. So we'll get lambda 1 star minus lambda 2 times the inner product of v2 is equal to 0. So what does that mean? That means is either this equal to 0 or this equal to 0. So let me say lambda star minus lambda 2 is equal to 0. So that means that lambda 1 star equals to lambda 2. But remember, lambda 1 star is lambda is real because it's an eigenvalue of an Hermitian operator. So that means that lambda 1 equals to lambda 2. But that is not possible because we assume that they are distinct, they are different. So what's the second possibility? Is that v1 equals to v2 equal to 0, which we need. So that means that they are orthogonal. Now what does that mean? That means if we have a set, for example v1 and until vn, if you remember that we face a lot in this case, that we have a set, the eigenvector. If you remember in this the infinite square rule, we have the sign n pi over a or something like this. So these are eigenvectors, different eigenvectors. So this theory guarantees that if they have different eigenvalues, so they are orthogonal. So this is a mathematical way to show that these indeed must be orthogonal. But inshallah, we'll discuss these details in chapter 3. And thank you for watching, and inshallah, see you soon.